Good morning, physics students. Welcome to week 8 of quarter 2. We only have a few weeks left. This week we are going to start the week by talking about things that move in a circle at a constant speed or a constant velocity. We are going to do a little lab station in which we have a flying pig that we're going to be able to calculate the speed of it. But just to illustrate, I've got this bucket full of protractors, things that move in a circle at constant speed. This would be one. All right, looking at the notes. In order to find the velocity of things moving in a circle, what they did in order to come up with an equation specifically for circles, they took our old equation, the v equals delta x over delta t. That's the old equation for constant speed, things that move at a constant velocity, and they put in pi because it's working with circles. So in order to calculate the velocity of an object moving in a circle, and we just have to understand that it moves at a constant velocity, it is 2 times pi times r over capital T. All right, we've officially made it to the back side of our equation sheet. You will find this on the very top of the back side. Capital T, it's just kind of like delta T. It means time, but it gets a special name in circular motion. It's called the period. Think of it as the time period. It is the time it takes to make one revolution of a circle, and that will always be measured in seconds. So still in seconds because it's time. R is the radius of the circle, and it's a distance. Radius is a distance, so it has to be measured in meters. All right, once we know the velocity of the object moving in the circle, we can also find the acceleration of an object moving in a circle. And this has a special name. It's called centripetal acceleration. It gets a little C next to it. It stands for centripetal. I like to think of it as circle. So if you see of AC, it means you're looking for the acceleration of the object moving in the circle, centripetal acceleration. The equation for centripetal acceleration, AC, centripetal acceleration, is equal to v squared over r. V is the velocity, has to be in meters per second, and r is still the radius, and it still has to be measured in meters. The neat thing about circular motion is objects can accelerate even though they're moving at constant speed or constant velocity. And that is because it technically, by its definition, acceleration is a vector, which means it can have a change in speed or direction. It doesn't change speed, it moves at a constant speed. That's what we're dealing with here, but as it moves in a circle, the direction is constantly changing the entire time. So technically, it's accelerating. Objects can accelerate by changing speed or direction. In the case of a circle, it's the direction that's constantly changing, which causes this centripetal acceleration. Once we know the centripetal acceleration, we can also find the centripetal force. We just use this old force equation, F equals ma, and they put little c's next to it to represent centripetal. I think of it as circular force, but the technical term for it is centripetal. So Fc, centripetal force, and then the A becomes AC from up above, centripetal acceleration. So the equation for centripetal force, Fc, equals mass times AC. The neat thing about this is, just like before, we can cram two equations together to make a more useful equation. So if we take these two equations right here and we substitute what AC is equal to, v squared over r, and we plug that in place of AC, we get one more equation for centripetal force that is much, much easier to use because if we want to use this equation right here, we usually have to first solve for the AC, the centripetal acceleration, and then the FC. But if we dump what AC is equal to right here into the actual equation, we then can do it in one step. So here's a second equation for centripetal force that just combines the two, making it more useful. Fc, centripetal force, is equal to mass And then in place of AC, we take what it's equal to, V squared over R. All right, this is the equation that we will use more often than others. Centripetal force has to be measured in newtons. It's still a force, so the unit is still a newton. M still stands for mass, and it has to be in kilograms. V is still velocity, and it still has to be in meters per second. And the R still represents the radius of the circle, which is a distance, so it's measured in meters. All right, so just to recap, we kind of have 3 to 4 new equations, mainly 3 that we use to find the velocity or the speed of an object moving in a circle at constant speed. It is V equals 2 pi R over capital T. Capital T is the period, the time it takes to make one revolution of the circle. Then to find the acceleration of the object moving in the circle, AC, you just need to take the velocity squared divided by the radius. And finally, centripetal force, 2 technical equations, but the more useful one to find centripetal force, you just take the mass times the velocity squared over the radius. All right, the difference between centripetal force, which is what actually the force that keeps an object moving in a circle, and centrifugal force, which is this feeling of getting pushed outward when you take a turn, like in a car when you're driving and you hook a sharp left, you feel like you get pushed outward. Or if you ride an amusement ride, if you're on the swings, you're going like this, you are actually have a centripetal force, the actual swing holding on to the ride, pulling you towards the center of the circle, but your body feels like it gets pushed outward. That's the centrifugal force. All right, so the force required for circular motion is called centripetal force. We just learned the equation in order to calculate it. That is the force towards the center of the circle that keeps an object traveling at a constant speed along a circular path. This centripetal force produces the acceleration towards the center of the circle, and that can be seen. So if I move this in a circle right here, that centripetal force is my arm holding onto the handle. There's a force that keeps that bucket in place so that it doesn't go flying off. If I were to let go of it, get rid of the centripetal force, it would go flying away and it would not remain moving in a circle. Let's say you're riding in a car that suddenly takes a sharp right. Which way do you go? So if I'm driving in a car, it goes to the right. I feel like I get pushed out to the left. You seemingly push to the left as the car turns. It's often called centrifugal force. It is not a real force because there's nothing actually pushing you outward. It's simply inertia. All right, so your body wants to maintain its state of motion. You're driving straight, the car turns right, your body still goes straight, but instead it feels like it's getting pushed outward to the left, and that is technically centrifugal force is what people call it, but it's really not a force, it's just inertia. It's your body wanting to maintain that motion. So the difference between the two, centripetal force is the force towards the center of the circle. It's needed to keep an object moving in a circle. For my bucket, it was the handle I was holding on to. For the planets around the sun, it's gravity pulling inward towards the sun. Centrifugal force feels like an outward push, but it's not an actual force. There's no actual push there. It's just inertia. And then we already answered this up above, but I just wanted to make sure that you recognize it. When an object is moving in a circle at constant velocity, how can it be accelerating? A quick reminder that acceleration can be both a change in velocity or a change in direction. So it is changing direction. All right, this concludes the notes part of it. From here, I'm going to move my camera. I have a flying pig. I'm going to go get that set up. We are going to watch this pig fly around in a circle. We are going to measure the radius of the circle and the capital T, the period, the time it takes to make one revolution. And then we are going to be able to use our equation to solve for the velocity of the pig. All right, so I'm going to pause, get it set up, and then we will come back up here and kind of walk through some of the problems before we go. All right, 5 revolutions, and then just to average it, we're going to divide it by 5 to find the capital T, the period, the time it takes to make 1 revolution. There is 1, 2, 3, 4, 5. So I found it to be 11.3 seconds. 11.3 seconds. All right, that was for 5 revolutions. To find the time to make 1 revolution, we just have to divide that by 5. The other thing that we need to find is the radius of the circle for this pig right here. Okay, for the radius, what I'm going to do is, for me, it's easier to measure the diameter, the full distance from there to there of the circle, and then divide it by 2. So I'm going to take a step back. I'm going to put this on the edge of the path, and then on the edge of the path over here, and I find that the diameter of the circle is 0.8 meters, 0.8 meters, which means the radius would be half of that. It would be 0.4 meters. Okay, so I am back up front. We just collected our data. We got to see our pig flying in a circle at constant speed. We found the radius to be 0.4 meters, and we found the time it took to make 5 complete revolutions was 11.3. If I divide that by 5, I get 2.26 seconds. This is the number that we need. This is the capital T, the period, the time it takes to make 1 revolution. I don't want this number. I do want the number for just 1 revolution. I just wanted to average it to make sure it wasn't bad data. All right, for number 1, you're going to calculate the velocity the pig flies in meters per second, and then you're going to convert it into miles per hour. So V equals 2 pi r over t, velocity of an object moving in a circle. You're going to use this right here in order to calculate the velocity. Once you have it in meters per second, you're then going to do a 2-step conversion in order to change it to miles per hour. From there, you have 5 more problems to set up. Some of them are going to involve velocity, some are going to involve centripetal acceleration, some of them are going to solve for centripetal force. So we're going to set up the first couple together just so you kind of get an idea of how it works. Number 2, let's say your pig travels in a circle at 2.5 meters per second. That's my velocity. So V equals 2.5 meters per second. If he has a mass of 0.3, so my mass is 0.3 kilograms, and the radius of my circle was 0.9 meters, calculate the centripetal force. So I am looking for the centripetal force as my unknown. So I scan my equations on the front side or on my equation sheet, and I look for centripetal force. Fc equals, you can use either equation for Fc, but if you use the smaller one, you have to first solve for AC. We don't want to do that. We just want to use the one equation that does it in 2 steps. That is the m times v squared over r. All right, you're going to plug in your numbers, and you're going to be able to solve for the centripetal force. For number 3, for this, you're riding the swings at Mall of America. You hit a top velocity of 4.8 meters per second. At this speed, it takes you 24 seconds to make 3 revolutions. How far away from the center of the ride are you? All right, so for number 3, I'm going to switch colors. My velocity is 4.8 meters per second. It takes me 24 seconds to make 3 revolutions. Okay, I don't want to know how much time it takes to make 3 revolutions. I want to know how much time it takes to make 1 revolution. So I need to take the 24 seconds, divide it by 3, and I get t is 8 seconds. How far away from the center of the ride are you? So I am looking for the radius, the distance to the center. That is my unknown. All right, looking through my list of equations, the only equation with that capital T in it is my V equals 2 pi r over t. You have to be careful using your calculator whenever you use this pi. So I'm just going to help you set one up so you see, and then I'll turn you loose to work on the rest of them. If the velocity is 4.8, 2 pi times my radius, that's what I don't know, divided by 8. The first thing that I have to do is multiply the 8 to the other side. And I get 38.4. And that's equal to 2 times pi times the radius. From here, if I'm going to use my pi button, when you divide the 2 pi over, you have to put it in parentheses, the 2 pi. So if you're going to take 38.4 divided by 2 times pi and just use the pi button, you just have to remember to put that in parentheses in order to do it. Otherwise, your calculator does its order of operations different than you want it to. Okay? If you are just going to, you can also take 2 times pi, get it down to one number before you divide if you prefer to do it that way. Either way works, but when you do your math right, you should get 6.1 meters. So please check that for me, type that into your calculator, make sure that you can get that to work. All right, from there, you are going to solve for period. Ooh, that's on the bottom, so you're going to have to use your math right. Then you're going to solve for mass. And finally, for parts number 6, you're going to work through a couple of problems solving for centripetal acceleration, centripetal force, and the period, the capital T. All right, hopefully this goes well for you, and I will see you back later this week in order to learn about gravitational attraction between objects. So, thank you.